analysis of SGD with biased gradient estimators. My name is Ahmed, and this work was done together with Sebastian Stich. Vanilla SGD crucially depends on the assumption that we have access to unbiased estimators. However, in some applications, we only have access to biased estimators, or using biased estimators is more beneficial, like in sparsified SGD, which is used in parallel optimization, or in zeroth order methods. We present a general framework for analyzing SGD with biased gradients, and our framework covers smooth optimization problems, and we give convergence rates for both deterministic and stochastic optimization cases. So suppose that we have an optimization problem in which we want to minimize a function f using SGD, and the gradient estimator that we are using in this problem is both noisy and biased. So specifically in our framework, we use separate terms to indicate bias and noise. So in the special case where bias is 0, we get back to the standard SGD problem with unbiased gradient estimators. And in the case where both bias and the noise terms are 0, we get back to a gradient descent problem. We have also two main assumptions on the upper bound of the noise and bias terms. And these two assumptions basically characterize the noise and the bias. So the noise is characterized with two parameters, capital M and sigma squared, and the bias is characterized with two parameters, small m and zeta squared. So suppose this example of top K sparsification operator applied to a full gradient. So using this inequality, which is shown here, we can conclude that top K operator is actually a special case of our bias gradient oracle. And in this case, the small m parameter is equal to d minus k over d, and zeta squared is 0. We also analyze the convergence rates of our framework under different levels of convexity. For example, here I'm presenting the main theorem for the convergence under PL condition. So if the function satisfies the PL condition with parameter mu, then we have the following convergence rate. And you can see that this rate unifies both the rate for the deterministic case and the stochastic case. For example, if we are in a deterministic scenario, then sigma squared is 0, and we get a linear convergence rate. We also show that we can only converge to a neighborhood of the optimum point, and the size of this neighborhood is in the order of zeta squared. So back to the top K sparsification example, there we saw that zeta squared was 0, and this means that top K operator in the deterministic case can actually converge to the optimum point. You can also see these 1 minus m terms in our convergence rate, and since the m parameter is always smaller than 0, smaller than 1, this shows that we have a slowdown in our convergence rate due to the bias. We also discussed 4 different examples in our paper, and we show that those examples can be considered as special cases of our framework. And we analyze those examples both in the deterministic and stochastic cases, and I encourage you to look into our paper to see more details of this. So to conclude, we present a general framework to analyze the convergence of SGD with biased gradient estimators, and our theoretical results are quite generic, so therefore in some of the special cases our results are worse than the prior results which were tailored to those cases. And we believe that there are more methods that can fit into our framework.